welcome to the Colloquium talk today. And the speaker today is Dr. Henning Braunisch. And Dr. Braunisch completed his PhD from MIT in 2001. And he is now the principal engineer at Intel Corporation in Chandler. And his research area are in advanced microelectronic packaging and applied electromagnetics. And he holds 33 US patents, and he also received the Best Paper Award twice from ECTC. And he also received twice the SRC, GRC, Manhope Kang Outstanding Mentor Award. And he is also an affiliate professor of our department. And the title of his talk today is High Bandwidth Microprocessor Packaging.
Thank you very much. Thank you very much, Professor Seng, for the introduction. Welcome, good morning, everybody. As Professor Seng said, I'm going to talk about microprocessor packaging. So I will explain to you a little bit what is packaging and then talk about the electrical interconnects that connect these microprocessors together. So just brief background. Professor Seng already briefly mentioned it. I got a master's originally from Michigan State. I studied in Germany, and I came over here for a year. And I worked with Dr. Nyquist at Michigan State. And actually, this is my first publication from back then. I worked on electromagnetics. This has to do with something called leaky waves. And then I went back to Germany, and I worked on transmission line systems under Professor Grabinski at the University of Hanover in northern Germany. And then after that, I left my home country, and I came to this country to finish a PhD at MIT. And I worked under Professor Seng's own advisor, which is Professor Kong. And I had a thesis, and it was called Methods in Wave Propagation and Scattering. So the whole thing dealt with electromagnetics. I also worked at a research institute on the East Coast in Connecticut. It's called Schlumberger-Doll Research, where they do research in geophysical exploration. And I did some work on inverse modeling with Dr. Habashi over there. And then I joined Intel, and I moved to Arizona. And so I've been there since then, and I work on this microelectronic packaging, which was something totally new for me. I've been there now for 14 years. And I basically overview some of the work I've done since then, essentially going along some of the work. It's essentially talking about different topics in microprocessor packaging, and all focused on this high bandwidth interconnect problem. So I'm going to talk about some of the trends first, then discuss high density microelectronic packaging. So this density problem is one of the key problems in this area of the semiconductor packaging. And then I want to introduce a concept called coreless packaging. And after that, I'm going to talk about some of the metrologies that are very useful in this area. This has to do with microwave metrology, using something like a network analyzer to characterize the structures and materials that we build in these packages. And then I have an interconnect architecture, which is something like an information superhighway between chips, which is called a flex circuit chip-to-chip interconnect that we investigated a few years back. I will also discuss a project we did here with the University of Washington, where we talk about the effects of roughness that is affecting signal propagation on our interconnects. And then finally, we have another project which is a much tinier interconnect than the ones I had earlier on. This is called a silicon bridge, where we can make very high bandwidth interconnects between two chips that are placed next to each other on the same package. And so this is something new. And let me talk about some of the trends here. So in the past, when I first joined Intel, like around 2001, 2002, what people were still talking about was the fact that the clock frequency of our microprocessors that go into our PCs and our servers and so forth, they would typically double every 2 years. So when I first joined Intel, we were still brainstorming, how are we going to make a microelectronic package for something like a 20 gigahertz CPU that would be clocked at 20 gigahertz. So actually, as it turned out then fairly soon, if you scale your clock frequency, you have to scale the power of this CPU, or central processing unit, and it is also then scaling exponentially. So actually we were still talking about, well, how could we make a microprocessor and cool it if it were supposed to consume something like 1 kilowatt, like a 1,000 watt microprocessor? How would you do it? Fairly soon discovered this is not going to be practical. So it seemed like this whole Moore's law that people have been talking about and taking advantage of may come to an end because we won't be able to cool our processors. But then luckily people came up with a new concept, which is called multi-core processors. So instead of basically scaling the frequency at which you run these CPUs, which is sort of the engine of your whole system, instead of running it faster and faster, you put in more engines in parallel. So essentially you go after parallel processing rather than processing everything faster on a single core. And this basically enabled us to cap the total power that a microprocessor is consuming. So today, if you look at a high-end system, say a high-end desktop computer, you may run it at like 100 watts on your CPU. And basically, we've been able to keep it that way for the last several years, like 7, 8 years. We were able to keep that maximum power constant. And then you have other systems, such as your laptop computers. The CPU may be running at 30 watts, and that's it. We're not scaling that any longer. But instead, we're doing the multi-core processor. So it started with a dual core, then there was a quad core, and very soon we're going to see some octa-core processors coming out. And so that enables you to keep scaling the performance, but keep the total power of the CPU limited. It was also referred to as that we took a right-hand turn. Instead of scaling the power higher and higher, we took the right-hand turn, and now we're scaling the number of cores. But actually what happens is there's one metric that affects the whole system, and then this package that surrounds the silicon, it still continues to scale exponentially. If you want to have exponentially scaling performance, you will have to bring in the data that the processor is computing on in and out of the processor, also in an exponentially scaled manner. So this is referred to as input-output bandwidth. Basically, information in and out of the processor will continue to scale, and it becomes a big interconnect problem, which is what I'm mostly discussing in this presentation. So you're able to keep your power constant, your performance is scaling, but then your I/O bandwidth will continue to scale, and it essentially becomes the new limiter of your system, or potentially, if we don't do novel things to improve the I/O bandwidth. To give you like a quick example, so what we're talking about these days are bandwidths in the order of a terabit per second. So you know about gigabit, then a terabit is 1,000 gigabit, and essentially beyond that, you're going to look at petaflop systems and even exaflop systems. So it goes always in 3 orders of magnitudes going forward. And if you look at the power numbers, if you look at the memory that may be in your laptop or in your PC, there's something called DDR memory. And if you look at the power efficiency it takes to move information in and out of your memory, you may be looking at something in the order of 30 milliwatts per gigabit per second. So this is a power efficiency metric. So that sounds fine, but if you then scale it up to the whole system, you can see a milliwatt per gigabit per second. This is equal to a watt per terabit per second. So quickly, you're in the order of 30 watts per terabit per second, which means if you take that times 8 and you want to do a terabyte per second type memory, it would then consume already 240 watts. And quickly, you're again looking at a system that is consuming so much power that will be very challenging to cool. So now it's not due to the clock frequency, but just due to the sheer amount of information I have to move in and out of the processor, where we will hit a power wall, and this is now considered to be the I/O power wall. So what you need to do about it is basically improving this I/O power efficiency by a very significant amount, so preferably by an order of magnitude. What we need is to reduce this to single-digit milliwatt per gigabit per second. It's also referred to as picojoule per bit, which is equivalent in terms of the unit, or even sub-picojoule per bit for this interconnect. So 10 to 100 times better than what we may have today. So what are some of the things we can do? So basically, one of the things is that for many of the interconnects, it turns out that they are actually running a little bit too slow. So we will have to run some of these interconnects faster because the optimal power efficiency occurs at a higher speed. So if you look at the power consumption as a function of the speed that you run the interconnect, it is essentially some sort of a bathtub curve. If you run it too slow, you're not really transmitting any information, so you're dividing by 0, you're consuming a bunch of power for basically not transmitting anything, then the efficiency is bad. If you run it too fast, again, you're running into limitations similar to clocking too high. So if you run it at a too high a speed, again, you're consuming a lot of power just due to clocking, and somewhere in between there's always an optimal power efficiency. So we will see higher signaling rates to hit those optimal power efficiencies. At the same time, we need to do design and design a broadband high-speed interconnect. And another thing is that typically the chip and the package designers don't talk much to each other, but going forward, they will have to collaborate closely to optimize the overall, what is called a channel. If you send information from point A to B, there are circuits, and then there are the packages that are in between it, and everything needs to be optimized together. To give you an example, traditionally, when we look at transmission lines, you may talk about like a 50 ohm transmission line design. So the circuit designers say, okay, we're going to design towards 50 ohm, and they do their own work. Then the package people or system people, they design transmission lines, and everybody agreed, let's just make it 50 ohms. And then that's pretty much the collaboration that they had. The chip people sent the chips over, and then it will all be connected together at 50 ohms. So this is called impedance matching. So that was pretty simple. Then people came up with another thing after that. They said, okay, there's too much interference between the transmission lines. They came up with something called a differential interconnect. Again, there was a little bit of agreement between people. We're going to do it now differentially. We need the differential circuits. We're going to put the differential transmission lines. And that gave a big improvement. Then the next one is low loss interconnect. I will talk a little bit about it. And then further out, we don't know. There may be some new technique, and I have a slide at the end to give you something brand new that may be next, where the circuit and package people will work very closely together to improve the I/O power efficiency dramatically. Then finally, so what are some of the things that are important for this problem? So we talk about novel packaging architectures. I will have some of these here. Structures and also the materials, low-loss materials, they can help as well, but it is not the only thing that helps. Then designing for power efficiency and also use of computational electromagnetics. We're still limited today by the algorithms. They cannot be fast enough to solve some of the design problems that we have. And also metrology becomes more and more important because you need to characterize things more accurately. If you want to squeeze out the best power efficiency and optimize these systems, you need to know your materials very well, and so the metrologies are very important as well. Okay, so let me talk a little bit about what is here called high-density microelectronic packaging. So first of all, I wanted to show you a picture of a typical microprocessor, what we call the package. So essentially, you have something called the package substrate, which is this green square here, which is also shown here in the cross-section. It actually is a basis for holding the piece of silicon that is made in a fab. This is housing your CMOS circuits. And then at the same time, it has this lid on top of it, which is used for cooling the silicon. So in the cross-section, you can see here, there's this big thing. It's called a heat spreader. And the heat itself is dissipated inside of the silicon. So the heat can spread out, and we can then cool this using some kind of a heat sink. And the information that I was talking about, it has to flow in and out of the silicon through this green piece, which is the package substrate. And in this case, I also show a socket. So if you talk about high-performance systems, such as servers that go into data centers, perhaps at Google, Facebook, or any of the others, and then also into supercomputers, all of these have sockets so that you can easily upgrade these CPUs if you needed to. It is always a modular approach. They like to plug in these processors at the last minute, or they may have to replace them or upgrade them. And so we always have the socket. So this then becomes actually a challenge right away. So let me talk about first about the basic density. So this package, other than doing the thermal management, allowing the information to flow in and out, and at the same time bring the power in and out of the silicon, it has to essentially make the connection of some very tiny connections here on the silicon, which are at a spacing of less than 200 micrometer. So there's really, you cannot actually see them with your naked eye if you look at it. You have to use a microscope to just see the connections that are between this piece of silicon and the packaged substrate. It has to bring out those connections to a scale of around 1 millimeter, which is what is a practical scale for these sockets from a mechanical perspective. So essentially there's a space translation by a factor of 1 to 10 between the silicon and then the socket which is connected to the board. Another technique is called a ball grid array, where you use soldering to make these connections. Again, there's a 1 to 10 translation. So you have to make all of these connections. There's an example shown here from an actual real microprocessor package design, where you see all these transmission lines coming out. There's some circuits down here which are the connections from the chip to the package substrate. And you have all of these lines coming out. This may be like a memory bus that is connecting to the memory that is on the motherboard. Okay, so as you do that, this green piece, which is what we're working on in our research, is actually very complex in design as well. It has many layers. It can have 10 metal layers or even up to 20 metal layers for some of the server packages. So you do not only have this horizontal, what is called routing, but you have to go down through all of these layers, and there are always these vias, and they basically cause you problems in terms of signal integrity. There are some parasitic capacitances associated with these vias, and all of that limits your achievable bandwidth. And for the mechanical purpose, you can see there's actually this piece of packaged substrate, which looks like a piece of chocolate essentially. It uses similar materials that are used for the motherboards, which uses something called FR4, but it is all miniaturized. But in principle, it is similar. So what happens is there is a thick layer at the center, which is called the package core. And you have to get through that core using vias that are much larger than all the vias that are on the surrounding layers. And again, this is there to provide mechanical support to the whole package. But electrically, it has bad performance, and we need to deal with these so-called plated through holes. And then this socket itself has problems because these pins, they go through the socket body, and there can be interference between the signals. This causes crosstalk. And ultimately, another issue are some capacitances that are associated with the silicon itself. There's something called ESD protection, electrostatic discharge protection, and they put some diodes there directly at the output of the I/O lines. There's right away a huge capacitance that limits our bandwidth as well. So these are all some of the contributors that limit our bandwidth. Now, let's take a closer look here. So this is a standard package substrate in cross-section. And you can see there are some of these layers. This is actually really oversimplified because I mentioned there can be 10 to 20 layers on this package. This is housing all of these transmission lines I was showing, and also there are layers to provide the power and ground to the chip. And then you have to get through this thick core, which is really there here to make this very stiff mechanically. Because I have to put these tiny connections on top of it, the thing has to be super flat so I can make all these very fine connections. If there was any warpage, I wouldn't be able to make the connections at such a fine pitch. I would get open connections and the whole thing would not work at all. So that's why they have this thick core. It's around 800 micrometer or 0.8 millimeter thick. Ideally, from an electrical perspective, we would like to get rid of it. So there's a trend towards core-less packaging. And this is something we investigated in my research group a while back. And one thing you can do, you can try to make this smaller. These are called micro-plated through holes. And then ultimately, we would like to have a coreless package. Now, this one may be pretty bad because, as I mentioned, the mechanics are also important. So this could be very, very thin at this point, maybe only 200 micron or 100 micron. It has only these thin layers, which are called built-up layers. So this may not work from a mechanical perspective, even though it would be great to have it electrically. So what we came up with is a different approach. It's called bumpless built-up layer, BBUL package. So what we do in this case, we actually could make a effectively coreless package electrically, but we still have a core. And what we did is we took a core, which is the same material as what you have here, and we're embedding the die into this core material. And then there's a process flow that allows us to build up metal layers directly onto this silicon die. and fan out the signals, which is what I still need to do. I need to do the space translation. Remember, 1 to 10 to go from 200 micron connections to about 1 millimeter connections. And do it this way, essentially. So now this core here, which is next to the die, provides you mechanical integrity, and we can bring out the signals and the power in with very good electrical performance. Actually, this had already been around. The additional thing you need to consider is the thermal management. So what we achieved here is actually to expose the backside of the die to the rest of the system. So you can, when you look at the package, you actually see the silicon itself here, so that now you can also effectively cool it from the back. If you were fully embedding this into something else, then you would have a thermal problem. But this one is a package that has all the attributes. It has mechanical integrity, it has good electrical performance here in the front side, and the thermal management can be done on the back. All right, so this gives you some idea about what we do. We have a lot of interaction between different engineers. We have mechanical engineers, electrical engineers, materials scientists, and so forth. And they all work together to come up with something like that, perhaps. Okay, so now let me switch gears into something totally different. So something purely electrical. Actually, this is microwave engineering. I want to talk a little bit about characterizing transmission lines, because for the signal integrity problem, we constantly have to design all of these transmission lines, study their interaction, and study the materials that we use to build these structures. We need to be able to characterize transmission lines. And since I'm going to use this later in this talk, I want to briefly tell you how we do this. So this is called a de-embedding problem. So what you can do, you can build a transmission line, which is kind of schematically shown. It has a length of L. And what I have are some microprobes. They're called GSG microprobes that can land on these probe pads that I show here. And there's a pad surrounding your signal pad, which is all grounded to an underlying ground plane. So this would be something like a microstrip line. So the problem is I can make this measurement, but when I do the measurement, I will also measure the effect of these launchers or pads at the two ends. What I really want are the properties of this transmission line. So take out the properties of the transmission line from this overall measurement is called the de-embedding problem. I want to de-embed the properties of this transmission line from the overall measurement. And it turns out this is kind of interesting. So if you do your transmission line theory, you know transmission line is characterized by a propagation constant gamma. It has a length L, and it has a characteristic impedance Z. I would like to know this gamma and the Z ideally from my measurement. And what we really measure is a cascade. The total measurement, M, is a cascade of the S parameters or scattering parameters of these launchers cascaded with the transmission line. And so if you look at this, essentially because the launchers at the two ends are the same, and there's something called reciprocity, which means S12 is equal to S21. There are three unknowns, complex unknowns for this launcher, and I have two more complex numbers I need to find. There are really 5 unknowns I have. I don't really want to know these launchers, but they're still not characterized either. So I need to have I need to find 5 unknowns. It turns out I can make measurements here, and I can measure essentially the S11, the return loss, or and also the insertion loss for this overall system. When I make one of those measurements, I get basically 2 equations, but I have 5 unknowns. So what can you do? What people then basically say is I can make, so you can write down all of these equations and basically calculate what are the S parameters for this overall system, and there's basically 2 equations with 5 unknowns. What you do then basically is you proceed and you build 2 structures. You build one transmission line, and then you build a transmission line that is perhaps twice as long, and we call it LA and LB. You make a short one and you make a long one, and you measure both of them. So now you essentially get 4 equations for your 5 unknowns. Then you say, well, that's really not enough, it seems, if I think about my linear algebra background. But it actually turns out, when you study the equations, that these 4 equations can be solved, however, not for all of the 5 unknowns, but at least for one piece of it, which is the propagation constant gamma. And I call it the implicit de-embedding, because essentially it throws away it gets rid of all of the unknowns, the 3 unknowns in the launchers, and also it does not give you the characteristic impedance, but it does give you the propagation constant. There's no approximation here at all. You use the S parameters of the short line and the S parameters of the longer line, plug it into this function. There's an inverse hyperbolic second function here, and you just calculate this, and it basically spits out the propagation constant, which was originally buried inside of your little system here. And we can get this without any approximations. This turns out to be very useful, and I'm going to use it later on, so that's why I wanted to show you this one. It's a closed form solution for the propagation constant. So let's use this in something for making our interconnect better or characterizing our interconnect. So if I look here in cross-section, this is a microstrip line. One very typical problem we have is we would like to know the dielectric constant and the loss tangent of my substrate. And perhaps from cross-sectioning this structure, making some measurements, we already know the geometry. We know the width and the thickness of the line. We know the thickness h of this substrate. And we also know the conductivity sigma of the metal, which is, for example, copper. And you can always measure that using a DC type resistance measurement and find out what the conductivity really is. Because copper is not really copper in reality. Often the conductivity is quite a bit lower than that of pure copper. But in any event, so those things are basically considered known. So we want to find out what is the dielectric constant and the loss tangent from making a transmission line measurement. So we're going to make exactly the measurement I was talking about. We built 2 of these structures, and we can use the implicit de-embedding that I was just explaining to find the propagation constant. The propagation constant is a constant number. The real part is called alpha, the attenuation constant, and beta, the phase constant. And so from my measurement, I get basically alpha and beta with very good accuracy because the de-embedding has been taken care of analytically. I also know my geometry and the conductivity of the metal. So what I can then do is a very simple called parametric inversion. I use an electromagnetic field solver. In this case, it's a 2D problem that I need to solve. And I can put all this information into my inversion algorithm. So essentially, I can predict the alpha and beta for a given dielectric constant and loss tangent using an EM model. And that can be done very accurately. And since it's a 2D problem, it is solved very fast. And then essentially I use a Newton-Raphson algorithm. It's a nonlinear solver that basically now makes an adjustment based on my measured alpha and beta. I go ahead and adjust my epsilon and tangent delta to make a better match with my measurement, which is the alpha and the beta. And so I go back and forth in a loop, and quickly it converges to a solution for the dielectric constant and the loss tangent that will exactly match the propagation constant that I actually measured in my lab. So this way I can basically find the dielectric properties of the substrate based on my microwave measurements that I do in the lab. So this is one of the techniques we developed a few years back, and we use this to measure the dielectric properties or some related techniques. People have improved this. There's also a question about something called causality. And some of you who have studied electromagnetics, they know there's something called the Kramers chronic relations. And there is actually a relationship between the dielectric constant or the real part and the imaginary part of the complex permittivity. They have to have a certain relationship, which is essentially a Hilbert transform, so that the response of the system becomes causal. So you can build that also into your solution and make this actually better. So this is kind of interesting, and we can get our material properties from that. So now, again, a different topic. So this time I want to talk about a new architecture in packaging. So what I show here is a motherboard. And this could be a very typical, either a server that is put into a data center or some kind of an engineering workstation. What they typically have is they have more than one CPU. And there are 2 sockets here, these brown pieces. And the CPUs are placed in there, and they are supposed to communicate with each other. Today, how they do it is they have interconnect that runs through the motherboard. But to be able to do this, first you need to get through the package, as I explained earlier, then through the socket at about 1 millimeter pitch, get onto this motherboard. The motherboard doesn't have very good material properties. It's a material called FR4, which has a fairly high dielectric loss, which is what we just tried to measure in the previous slide. And also it is not a homogeneous material. Essentially, it has some fiber weave in it, which makes the material inhomogeneous, and it is not very good for signaling. You can think of driving your car from point A to B, and you have to go through some kind of a wheat field in between, which is like a really rough interconnect, and it slows you down. And in effect, it really does slow down the signaling in terms of the bandwidth. So what we said, okay, what we can perhaps do is bypass all of that. We build sort of a super highway that bypasses everything. We still need connectors because, as I mentioned, these sockets are very important to make our systems modular. So we designed some special high-speed connectors that we can place directly on the top surface of the package substrate. So now you get a path for your signals that is very clean, in the sense that your signals come out from the die, which is this blue piece under this heatsink here. They can travel across just the surface of the package, so I don't have to go through all of these vias in my package. Go through a special high-speed connector. This high-speed connector doesn't care about power delivery. The power will all come through your conventional socket. This has been purely designed for high-speed signaling, which is much better if I don't have the constraint of having to do low resistance and such. So it's just designed for high speed, and I go out on this flex circuit cable, and this can use materials that are much better than the motherboard. And so I can directly make a connection from point A to point B and get much higher bandwidth. So I'm going to show you how much better it is. We actually build something using active silicon. So one concept here basically is decoupled power and I/O, so which I already mentioned. So the power is going to come in vertically from the motherboard, and my information flows out horizontally off the package. It's a little bit like the human system, like you have a brain that needs to be powered up. So the power is probably going to come up vertically somewhere from your heart, and then all of your I/O is sort of horizontally. We don't do those things in the same interconnect. They are separate from each other or decoupled. So it's a little bit inspired by that. And so let's look at this flex cable. So this is a very simple construction. You have these microstrips. This is a cross section. They're sitting on a substrate. There's a ground plane, and you have these signaling lines. And we went ahead and built some of these. So this shows attenuation constant, which is this alpha I was talking about earlier, that we can always measure quite accurately using this de-embedding technique as a function of frequency. And so the red line here is FR4, which is the material the motherboard is built of. And you can see the loss goes up with frequency, reaches about 1 dB per centimeter at 20 gigahertz. And then we went ahead and built a couple of these. So first, we were not successful. Our original cable, because it has some materials in it, including some adhesives that hold all of this together, it ended up being lossier than the motherboard. But then we improved this little by little. Flex number 2 was better, flex 3, flex 4. So ultimately, if you look at this in terms of a bandwidth, you look at this 0.5 dB per centimeter line here, it costs us around 10 gigahertz for FR4, and we were able to extend this to about 30 gigahertz. So this cable has a 3 times higher bandwidth than your motherboard, roughly speaking, just for the cable itself. On top of it, we get the benefit of bypassing all of these discontinuities, including the socket. So then we worked actually with a large group within the company, including the circuit designers, to build some, at the time, really advanced high-speed signaling chips. And they were able to build circuits that can run up to 20 gigabit per second. That means you send 20 billion bits per second through one transmission line. And this is a plot that shows basically the achievable signaling rate as a function of length, the distance you transmit this information. And they build a system that is on FR4, but it can only go up to about 8 inches length. After that, you run out of signaling margin, and you cannot continue any more signaling. But using this so-called information superhighway architecture, we were able to extend the achievable length much longer, up to 20 inches, and then even up to 36 inches, which is about 1 meter or 91 centimeters, I believe, in distance. And so that is what basically you get out of cleaning up the interconnect, using better materials and a novel architecture to bypass discontinuities. So here's some more details of this work. So for example, 7 inches of FR4 running at 20 gigabit per second, which at the time was actually amazing that they were able to do that, which was an achievement of the circuit design. But then if we run it over a similar distance, a little bit longer on this flex channel, at the same speed, you can see essentially for this data point here, you say, well, it's the same, right? Same speed, same length. But the truth is that for this flex interconnect, you have a much better, what is called eye margin. So what you're looking at is called a signaling eye. It is something that is similar to what you could measure in the lab using an oscilloscope, only that this is something more advanced, which shows the bit error ratio as a function of the timing and the voltage that is used to do the signaling. And you can basically construct this called bit error ratio eye diagram. So the bigger this eye is, the better your signaling. And so this is quite a bit bigger and better. And what you could now do is reduce your voltages and turn this also into power savings, which is this big problem I was talking about at the beginning. And then if you look at those very long cases, 17 inches long and then 36 inches long, 91 centimeters, we can still do the signaling up to almost 20 gigabit per second, which is, roughly speaking, 10 times faster than your typical interconnects today. So you have something called PCI Express in your computers, and the typical one, Gen 2, runs at 5 gigabit per second, and they're working on something called Generation 3, which is around 8 gigabit per second. This is quite a bit faster. So this is what we can do in research. So let's see. Those connectors that we put on there to enable all of that, so I mentioned they were specifically designed for high speed. So the typical connectors that you can buy off the shelf, they have bad performance. This shows the insertion loss as a functional frequency. This is how much power can be transmitted through a connector. And we have a spec 1.25 dB at 10 gigahertz, and we needed to redesign this and make it much better. So you can see that these connectors that we designed were able to achieve the spec up to 10 gigahertz, much cleaner. And also for crosstalk, they are better. We want to get something of better than minus 35 dB up to 10 gigahertz, and these new connectors were able to achieve that. Okay, so here's another topic. This is something Professor Zhang here is very familiar with. This is the metal surface roughness problem. So when you look at these interconnects, again, this is a cross-section of a real interconnect. In this case, it is one of those flex cables. You can see that the copper in here is actually not smooth, but it is rough. And now again, this causes us some problems because of a very classical electromagnetics problem called skin effect. So at high frequencies, the currents that flow here in and out of the page, they don't flow through the entire cross-section, but they will be constrained to a thin layer at the surface. For copper, at around 5 gigahertz, it turns out to be about 1 micrometer thick layer. But actually, this copper is around 15 to 20 micron. And so you see the dielectric here is 75 micron thick. So actually, really, all these currents have to flow only at the surface of the copper. And what it then basically does when the surface is rough, they have to go up and down and follow all of these undulations on your surface, which makes the effective length, the currents have to travel much longer. It increases the resistance per unit length. And that, again, will limit your bandwidth, because simply speaking, bandwidth is 1 over R times C, resistance and capacitance. So if you have more resistance per unit length, you have limited bandwidth. So we're studying this rough surface problems for that reason. We need to understand it, what does it do to us, and so forth. We need good models for it. And so this is a modeling project. Essentially, the attenuation can be described as a combination of what is called conductor loss and then also plus the dielectric loss. The roughness will enhance essentially your conductor loss, as I just briefly explained. And so we have this so-called roughness enhancement factor that increases your attenuation. So it's always the question, how can I find this enhancement factor if I know the roughness? Once I can model that, then I can try to give people some guidance. You need to achieve a certain roughness so that my interconnect still works. So this is what the problem is here in terms of engineering. There was a classical empirical formula that has been very popular, still being used today. It's called Hammerstedt-Becker, that have a very simple relation between the skin depth, which is essentially the frequency, 1 over square root of f, and what is called the RMS, root mean square, roughness of my metal surface. So you tell me how rough it is, and I tell you how much electrical effect it essentially has. However, this equation is not very useful for more detailed studies, because the description of the roughness is very, very simple, just a simple one parameter, that is the RMS roughness. As you can imagine, a rough surface is much more complicated than just one number. It turns out we need to talk about the spectral properties of this roughness, which is what we did in this research. So with work funded here at University of Washington, we developed this new model called a 3D small perturbation method, and we came up with a better model for this roughness. And so this time, instead of just putting in the skin depths and say the RMS roughness, we actually put in something called power spectral density, W, which is a much more detailed characterization of my surface roughness. So actually, the RMS roughness, RQ, is in there. If you take that spectrum and integrate over the full spatial frequency domain, you basically add up all of these spectral components, you end up with the RMS roughness squared. It's very similar to signal analysis. So if you have a power spectral density of a signal, if you just integrate the whole spectrum, you get the power or average power that is in the signal. Same here for these rough surfaces, it's just the spatial domain instead of the time domain. Then when we recognize that our roughnesses, if we stand on a rough surface and we are able to look into any direction and the roughness effectively does not change, because maybe my process that created the roughness is such that it doesn't care about directions, we can talk about an isotropic rough surface. In that case, this double integral can be simplified to a single integral, and we also have only a one-dimensional power spectral density W. So this model looks better. Actually, it looks a bit scary because of these infinite integrations and so forth, but the truth is, once you have obtained this power spectral density, which I will show you how to do it, it's a straight numerical integration. Just integrate it up and you get the answer you want. So there's no equations to solve. It has already been solved analytically ahead of time. So how do you get this power spectral density? Essentially, what we also had to do was develop a fast algorithm for doing this. So there's a simple technique called the periodogram that you can find in your signal analysis textbooks, where you take essentially Fourier transforms of your profile, and then you average together all of these Fourier transforms to get an estimate of the power spectral density. It turns out for the 3D problem, where the height is a function of two variables, it becomes very tedious. Because to make the image of these surfaces, we use something called an atomic force microscope. And you take a little piece of the surface and you scan it, and it actually takes a few hours to obtain one image. And if you want to use the periodogram method, it would mean take the fast Fourier transform of that, but then do that about 100 times and average all of those spectra together to get the power spectral density. So that means you have to obtain 100 images using the AFM, that microscope. So it would actually take weeks to finish. If a technician can take 2 or 3 images a day, then you end up being stuck and it's not practical. So we came up with this fast method that actually allowed us to get the same information from just a single image. And I'm going to spare the details here right now, but basically it means take 1D fast Fourier transforms along all the horizontal and all the vertical lines, which gives me a bunch of spectra that I now can average together, and it converges as well, and I can convert it into a 1D PSD using what is called the Fourier-Bessel transform. So then I have basically the PSD of my rough surface. And then we did some experiments to see, does our model, the one that has those infinite integrations, together with this characterization technique I just mentioned, does it work in practice? And so what we want to do is build ourselves, again, some transmission lines, make some measurements of that. We know the transmission line is rough. Then we can go to another lab, remove some of the materials, make an image of the rough surface, run that through our power spectral density estimation technique, and put this into our model. At the same time, we can compare this now with a modeled attenuation, and then enhance the attenuation we get from our model, which assumes the surface to be smooth, and then multiply that times the attenuation enhancement factor and actually compare that result with what we saw in the lab. This may be a little bit confusing, but let's see if this makes more sense after this one. So this is the part where we go and use the atomic force microscope to make an image. We can basically go and literally make a measurement. This is done in MATLAB now to visualize it. So you get a map. This is 25 by 25 microns of the metal surface we scanned using the AFM. And then I did some MATLAB magic to make it look pretty, put some artificial lighting and so forth. And we can compare this to an SEM, which is a scanning electron microscope, to qualitatively compare, does this image make sense that we obtained? This is 3D, this is just an image, but you compare it and sort of say, okay, it looks similar, so this data is a little bit more trustworthy. So we basically have now this height function as a function of x and y, and we can run this through the PSD, or power spectral density estimation, which is essentially a spectrum analyzer for rough surfaces. And it looks like this. When you do this, you have the power density as a function of spatial frequency. So right now this goes up to a frequency of 10 per micrometer. So what it means is that you have up to 10 periods in 1 micron. And it is basically corresponding to a period of 100 nanometer. And that means essentially we have pixels that are 50 nanometer in size. So if you had black, white, black, white, black, white, you would create a spike out here at the highest spatial frequency of 10 per micrometer. Similar to frequencies for time domain signals, these are frequencies for spatial signals. And as you can see, you have a lot of low frequency content, and it drops off at the higher frequency. So this part corresponds to slower undulations, and then up here you have very rapid changes in your surface, and we can capture all of this in this function. If you integrate it all up, you get the RMS roughness, which is what this very old model used as a single parameter, but we can use this full spectrum information and put it into our formula to calculate the effect of this roughness. Then we did this, so actually we compared this new model with the old model, and it turns out in this case they were relatively close with each other, but it also shows that our formula works. So this enhancement factor at low frequencies, it starts at 1. You have no skin effect, and there's no effectively no effect due to the roughness. As you go higher and higher, your skin effector is kicking in, and it causes you additional loss, and this is this enhancement factor. It goes somewhere up to the region of 1.8. Okay, and then we correlate this with our measurements. So as I mentioned previously, what you do is you make an EM model that does not have any roughness in it. You just consider everything perfectly smooth, and then you have the conductor loss, and you add on top of that the dielectric loss. So you get this dashed blue line here, which is the attenuation as a function of frequency for a perfectly smooth line in a model. And then we did the characterization of the roughness, we obtained the enhancement factor, and we can predict what the rough loss should be, and that is the, I believe, green line here. And then we can also go to the lab and just measure the attenuation directly without doing any modeling. And that is the black line. And you can see that these have a really good agreement with each other in this case. Now, this also illustrates the effect of this roughness. Why is this important, right? Why do you need to know all of these things? So it turns out that if the line is perfectly smooth and you look at a signal of 10 gigabit per second, which is what I was talking about earlier, we did 20 gigabit per second, this is example 10 gigabit per second. So your fundamental frequency is around 5 gigahertz, and maybe the upper frequency of interest is around 7.5 gigahertz, somewhere between the first and second harmonic, or the fundamental and the next harmonic frequency. So this is the frequency range of interest. You can see the roughness effect is actually roughly the same as the effect due to dielectric loss. So it is very, very significant. Just for, say, PCI Express generation 3, they need to worry about these things. Okay, so finally, here's one more architecture really fast. We have something called a silicon bridge. In this one, we built a package. Again, this cross-section, this is the top view. And we want to interconnect two chips that are on the same package, but do it at design rules that are much, much finer than what we can achieve on this package. And we basically use a piece of silicon that we mount there into the package. And we build some interconnect at 45 micron pitch, which is much smaller than what is typically used to connect die to package. And we can get very high interconnect density between two dies. And then again, you do some modeling. You can look at bandwidths, and what you find here, now you actually do talk about terabyte per second times of bandwidths. If you do some calculation as a function of the signaling speed, you find the bandwidth is around 1 millimeter times terabyte per second. This means you can send 1 terabyte per second of data through a bus that is 1 millimeter wide over a distance of 1 millimeter. And that is about the distance you need to achieve in this type of applications. That way we can actually connect, say, a CPU and a memory at terabyte per second bandwidth with each other without having to go anywhere to a motherboard or to some other module. This is very close integration, similar to what is called 3D stacking, where you put the chips on top of each other. This would potentially cause you huge thermal problems. Here we can have effective 3D stacking, but placing them next to each other. Some people call it 2.5D integration. Okay, and then finally here's something for you to think about. So I showed you these transmission lines. They're on a package. They all have some interference with each other. It's called single-ended signaling. You use one trace for one signal, and the next trace is right next to it, and there's some crosstalk between them. People went ahead and they found crosstalk will limit your bandwidth, so they improved it. They did something called differential signaling. In this one, they used two traces for each signal. You send a positive and a negative signal, and the interference between neighboring transmission lines becomes much less. This is called differential signaling, and you introduce some intended coupling that helps you to do this. And going forward, what we're working with, in this case, North Carolina State University, is something called multimode signaling. So we can push this and have something called collaborative signaling. We can have many wires together. In this case, for example, 4 wires that are coupled closely with each other. We can send 4 signals simultaneously using the 4 modes that exist on these 4 transmission lines. And that way, we can remove the crosstalk completely from this bundle. We may still have to worry about bundle-to-bundle crosstalk, but we can make this bundle bigger and bigger and ultimately eliminate crosstalk altogether. So this is a new thing, and clearly this will require some work on the circuit side, and this is where this chip package co-design comes in. If we all work together, then we can potentially achieve 10 to perhaps 100 times better power efficiencies for our future systems. All right, so this is what I had. Again, I had some new architectures. I talk about scaling of bandwidth, scaling of power, scaling of speed, characterizing the materials, and very important are novel packaging architectures where we basically go away from standard architectures such as motherboards and come up with some innovative ways of connecting things together. So that's what I wanted to share. Thank you very much.
Any questions?
Go on.
This kind of crosstalk, if you think about these days, people are working so much on the wireless MIMO design. Is there anywhere we can get some kind of channel information and crosstalk information that we try to compensate it back?
Yes, thank you for the question. So the question is if we could use MIMO, multiple input and multiple output techniques to improve channel performance and also eliminate crosstalk. Actually, it turns out conceptually this is similar to the multimode signaling, where, for example, we may have 4 inputs and 4 outputs, and actually they do interfere with each other, but we know the amount of interference or the mechanism of interference, and we can take care of it by signal processing at the 2 ends. That is my chip package co-design. So it turns out actually it's not exactly the same, because what we exploit here is called multi-conductor transmission line theory. Actually, we know our channel very well. In MIMO, typically you make no big assumptions about your channel. You know there's some multipairs and all sorts of crazy things happen. The channel is not very well known. Here we can know the channel very well by designing it, and we do additional things to bring the power down. So MIMO is very general and maybe power hungry, and we try to do this very efficiently by knowing the properties of those transmission lines. Thank you.
Questions?
Other questions?
One question, you look at the effects, measurements, you have a lot of oscillation. Why is there a lot of oscillations? It affects the line, the
Okay. So there's also some mismatches.
All these oscillations, what is that due to?
So in the 2-line method, you make actually one assumption that when you do the 2 measurements, you have a structure number 1 and a number 2. They are of different lengths. The theory assumes they're perfectly the same except the length. But there are some minute differences between them. Also, where you land those probes exactly in all of the measurements may vary a little bit. And so there's essentially a little bit of a mismatch between the measurements. And that, I believe, causes some of the ripples in here. Yep. Thanks for that. One more question?
What's the typical RMS roughness of the transmission lines, and then have you looked at CMP or other techniques to mitigate that?
So this is a really good question. The question is, how much roughness is there? So in this example, for example, the RMS roughness is in the order of 1 micrometer, actually 1.3 microns. What happens in these stacks, you can try to make it less rough, but in fact what we typically do is we roughen the metal intentionally to improve the adhesion between the layers. So it's actually a very challenging problem to improve the roughness. So there are some other techniques such as chemical adhesion techniques where you can make it smooth and you introduce some layer at the boundary, but that can also have some attenuation effects. So typically it is very rough to start with, but people are constantly trying to make it less rough and less rough. And so what we do is we try to give them some guidance how much smoother they need to make it. Like if you try to make it atomically smooth, you may be able to do it somehow, but it may be very, very expensive. Like CMP, for example, is known to be an expensive technique for planarizing surfaces. Okay, thank you. So,
Questions? Okay, thank you very much.
thank you for having me.